Welcome, everyone. As Ian has already said, I will be talking about some use cases that we have implemented on top of Samplomatic and the executive framework. Specifically, let me set the stage a little bit. You already saw on Wednesday that we have kind of ticked off the advanced classical mitigation tools on our roadmap. And in this presentation, I will basically show you what actually goes into all of that and how we've realized the implementations of these advanced tools using Samplomatic and Executor. This presentation will be done in two parts. First, I will walk through a hopefully common workflow that everyone is familiar with, probabilistic error cancellation. And then in the second part, I'll show two additional tools that you can implement using the same pattern of how we're implementing these frameworks, specifically adding shaded light cones to PEC and the new propagated noise absorption error mitigation method. So let's start with part one. What is probabilistic error cancellation? Well, essentially, it's a technique that allows us to mitigate gate noise by randomly sampling from an ensemble of circuits implementing the inverse noise channel. That's quite a mouthful. There's 3 steps to it. First, we have to learn the noise of our device, which you were already able to do with Noise Learner v2 in the past. I'll show you how Noise Learner v3 fits into the new framework that Ian has already alluded to before. Then in the second step, you need to implement the inverse noise channel and sample from it. And then in the third step, you need to reconstruct your mitigated expectation value that you're after in the end. You already heard from Tony on 2 days ago how this was done in the past, but now I'll walk you through the various steps that we need to take in order to implement this in the new framework. So Ian just gave a very detailed overview of how you use Samplomatic to build a template circuit and Samplex. Here, I will keep it very simple and use the tools that Samplomatic provides to us to do this basically automatically. So looking at some code, let's assume you have some target circuit and some target observable that you're after. What we're using now is this generate boxing path manager from Samplomatic, and we'll configure it to our needs to produce a boxed up circuit automatically. We wanted to box up gates, we wanted to box up measurements, and here we have some high-level configuration settings that allow us to configure these annotations that are being added to the box operations. So we enable twirling, we enable noise injection annotations for gates only, and here we use an inject noise strategy called individual modification. This is relevant for the shaded light cones that I'll get back to later. Basically, what this means is that all of our box operations will have unique identifiers on them, which we require for our shaded light cone computation. And then we also want to have annotations on the box that contains our measurements that allows us to specify the change basis rotation such that we can specify which Pauli observables we want to measure and not just always measure in the computational basis. And then we simply add this boxing path manager into the post-scheduling stage and run it to obtain a boxed up ISA circuit that we can run on the device. Now we need to learn our noise. And as Ian was emphasizing earlier, it is very important that you have this portability such that you can trust that the noise you learn is also the noise that you will observe when you are actually running your circuit. In Noise Learner v2, you didn't have the flexibility of configuring how the layers in your circuit are being identified, but in this new framework, you're actually able to do so because you are telling the Noise Learner v3 which are the layers that you want to learn the noise thereof. So we have our boxed up circuit. We want to extract the unique layers, so we don't want to learn the noise for these 2 layers twice because it's the same layer, and then we want to run that. What does that look like? There's a nice, simple, find unique box instructions utility in Samplomatic that we just provide the circuit that we just generated before into, and then we get back a list of unique layers, which we then can simply run through our noise learner at the bottom. And there's a bunch of options, just like you're used to with primitives from the past, that you can configure how the noise learning is actually being done. You can configure the number of randomizations, the shots. You have the layer per depth setting that you can configure. And then there's also post-selection subsection of configuration options, which I'll get back into a little bit later. Now, we are basically at the point where we've boxed up our circuit, we've learned the noise, and it's time for us to actually run it. It's very simple here. We just use the Samplomatic build function to generate our template circuit in Samplex. I'm not going to go into the details of that because Ian already covered this quite well. But let me talk about the post-selection step. So here we have an additional repository called Qiskit add-on utils, where we've implemented additional transpiler passes that allow you to add spectator and post-selection measurements, which allow you to have an additional classical register in your circuit by which you can then post-select shots in order to filter out cases where you had leakage in your state. So this is basically an additional error mitigation step that we can concatenate with the PC that we're trying to implement here. And what we basically do is we run our template circuit, because it's just another quantum circuit from Qiskit, through this post-selection pass manager to get a new template circuit. And I'm not showing the output of this, but basically it will just have additional operations appended at the end. What I want to emphasize by this is that the template circuit is a quantum circuit that you can manipulate further like you wish. And these post-selection strategies will help us improve our quality of our observable expectation value. And this is essentially the similar mechanism that the noise learner can do internally, which is the settings I mentioned earlier. And then finally, we also have another utility in Qiskit add-on utils, which we call get measurement bases. What this does is says, given a target observable that you're interested in, it will compute what is the basis input to the changed basis annotation that you need to provide to the Samplex. Because basically what that is, it is an encoding of specifying the X, Y, or Z basis for Pauli that we want to measure into an integer representation that is easier decodable for the Samplex. And then we have this reverser object, which we will need after the fact when we are trying to compute our expectation value in order to figure out which measurement basis corresponded to which Pauli that we were interested in. Step 4, it's time to simply run our experiment. This is fairly straightforward. We have our Samplex. We bind the inputs to the Samplex. Here we're specifying noise scale as -1, which means that we want to sample anti-noise in order to really cancel our noise for all possible inject noise annotations that we did. You could also unravel this into a dictionary to fine-tune the noise scale for different noise layers. But because we want to cancel the noise of all layers, we simply say -1. And here I'm inserting the change basis annotation. This is target observable in this example, has a single Pauli, which is we're just indexing the first element here. And now we are putting together the quantum program that Ian mentioned exists in the preview branch of Qiskit IBM runtime. We specify the number of shots. We can add a dictionary of noise maps on the outer level. You could also specify noise maps for every single item of your quantum program separately, but you don't need to resend the same noise maps over and over if you have multiple program items that you want to reuse the same noise model for, which is why we have the ability to just inject it at the top. And then Ian briefly showed this earlier. For actually constructing a quantum program item, we have our template circuit, we have our Samplex, we have the inputs to our Samplex, which we built before, and then we specify the shape, which means here we are going to do 1,024 randomizations of the Samplex, and then we have the chunk size and set up our executor and actually run it to execute the job. And now we basically are at the last step of post-processing, assuming everything worked on the hardware. We get the result, and now we have, again, in Qiskit add-on utils, we have a utility function that makes it a bit easier to compute expectation values. So I'll step through this one thing at a time. So we have the executor expectation values function, for which you basically provide a bit array of the results from your circuit's measurement output. You have the reverser object that I mentioned earlier, which is basically allowing us to map from which Pauli basis was measured into our observable. We have to specify what is the tensor axis that corresponds to our measurement basis. So this is the tensor manipulation that Ian was explaining earlier. if you have randomizations, or sorry, if you have parameters in your circuit, this axis might not be known up front in which position it will lie, which is where you can specify it. We have average axis. This can be, you will always be averaging over the shot axis, but if you have additional axes where you want to average over, this allows you to specify that. We have the measurement flips, which Ian already mentioned earlier. And we have some PEC-specific settings to know when to flip our sign based on the twirls that we have inserted. And we have the gamma scaling factor that we can compute from our noisy boxes in order to account for the PEC rescaling that we have to do. We have the post-selection mask, which is coming from our post-selector that we have. And then we have the rescaling factors due to T-Rex error mitigation. This is an example of trying to simplify the computation of your expectation values as much as possible. This is all open source, so if you have more elaborate needs, it's very easy to just go into this code and pick out the pieces that you need or modify them as you see fit. And this basically allows you to implement the full PEC workflow using the tools provided. So to recap, we use Samplomatic to take a target circuit and box it up. We have our Noise Learner v3 that allows us to provide only the unique instructions that we want to learn the noise of and then get the noise models that we have learned on the device. We use Samplomatic to build our template circuit and the samplex, which we then provide via a quantum program to the executor, and we can compute our expectation values using Qiskit add-on utils. This is the generic workflow. You see there's many moving pieces, but this is again emphasizing that we're featuring, well, we want to focus on capabilities rather than feature knobs that you can tweak, which are very rigid, which is why this whole workflow is very modular. Now, I will show PEC results in the shaded light cone part, which I'll be getting to now. But what I want to emphasize is how these two tools, shaded light cones and propagated noise absorption, that are now available, and you can learn about more later in this afternoon, they both rely on Pauli propagation methods. And I think this was briefly mentioned 2 days ago as well. This Pauli prop package is now available as well. It's in the Qiskit GitHub organization. It provides the classical subroutines that both of these methods rely on in order to efficiently perform the computation that these two methods need. What are shaded light cones? I think you've already heard this a little bit 2 days ago, but I think it's good to recap. So what we do is we have a circuit where we have our noise representations at every single layer. And what we want to do is we want to determine the impact of an error occurring in this layer, how it can impact our observable or our initial state. This allows us to bound the impact on our expectation value that we're after, which will allow us to say, do we actually need to care about the effect of this error in our PEC computation, or do we not care about it? If we don't care about it, that means it lies outside our light cone or has an additional shade that is basically transparent. Then we can remove this term from PEC and therefore reduce our sampling overhead. If we do care about it, it will basically have a bright color. You'll see that play a role in a little bit, and then we do need to care about it during the PEC sampling. And then in the final step, we have this local scales argument that I'll get to in a minute. You saw the full workflow for PEC before. Here, I've squished it a little bit, but basically you still have the 5 steps we had before. We box up our circuit, we learn our noise, we have our Samplomatic generation and our execution. And now you can see how the shaded light cone add-on fits directly into this workflow without changing anything around it. We have several steps as part of this workflow, which I'll step through in a minute in more detail. But basically, we have a forward bounding pass that we compute the effect of an error on our observable. We have the backward bound, which is determining the effect of an error on the initial state. And then we have a means to merge these two bounds together. And then when it comes to the time of executing this, we have this additional local scales argument as part of our samplex input, which this compute local scales function is fairly simply taking into account from the shaded light cone, where you have the merged bounds that we computed before and the learned noise. The local scales basically says that for every single error term that we have learned, you can fine-tune the effect of how much you want to scale it by. So earlier I was saying that in the sample, in the input to noise scales, I was just saying -1 for all of them, which means cancel all the noise that exists. With the local scales, we can really fine-tune this for every single error term that might occur in every single layer individually. And this is why it's important that we have distinction between the different boxes. So this is really not just for the unique layer one by one, but for every instantiation of every single unique layer. So this is quite a large tensor at some point. A subtlety that I want to point out is that we can actually perform this computation of our bounds before we learn our noise. And what that means is this computation can take some time, but we're not hamstrung by that because we can perform our noise learning and execution in fairly quick succession on the hardware because we can offset the cost of this classical computation to be done up front. The only thing that we need to know is we need to know what are the noise terms that what are the Pauli terms whose errors we are going to learn during the noise learning step. But how this is set up in our noise learner, we know that it's going to learn the 1-weight and 2-weight Pauli observables on every qubit in every single layer. So it's easy to predict what these noise terms are going to be and perform this computation up front. Okay, let's have a look at an example. This is a circuit of a transverse field Ising Hamiltonian, time-evolved, on 40 qubits for 20 Trotter steps, and then mirrored. What that means is that this entire circuit is basically a big identity, and this amounts to a total of 80 layers of 2-qubit gates. It would be hopeless to try to run a full PEC workflow on this case at the moment. But with shaded light cones, we can at least get some nice visuals in order to educate about the method. We're measuring a 3-weight observable, X, Y, Z, on qubits 10, 20, and 30. And what we have to do in order to still have, because this is an identity and we want our expected value of our observable to be 1, we also initialize qubit 10 in the +1 eigenstate of the X Pauli, or qubit 20 in the +1 eigenstate of our Y Pauli, and for the Z we don't have to do anything. But that's what these additional 2 gates here in the front are. Now, here I'm showing 2 light cones for this specific circuit. I'm showing one for the X era and one for the Z era. And I'll guide you through what this means in a moment here. So first, we compute our forward unequal time commutator bounds. These, because I'm showing the merged bounds, the forward bounds end at this red line. And you can see that when we look at the X era, the observable X, Y, Z, in the X case, in the very far right layer, it's actually commuting with this term, which is what that implies is that this X error happening in the very last step actually doesn't matter for our expectation value of our X observable. Not so much when we have a Y or a Z measurement. Conversely, looking at the Z error, it commutes with the Z observable, and the XY, not so much. You can see these characteristic patterns appear for these simple errors. Obviously, there's also 2-qubit errors involved here, but the plots get a bit more difficult to read, which is why I'm focusing on these 2. In the second step, what we can do is we can apply a speed limit tightening to our bounds. What that means is if we can only afford to compute our forward bounds up to this line, normally we would have a vertical block of yellow boxes going all the way to the left. But we know that if an error only appears here, the error appearing 1 layer further to the left up here cannot by any means affect this outcome here, which is why we can apply basically a speed limit on the information traveling of an error affecting our outcome, which gives us this angle on our light cone towards the edge. This is a very simple computation that takes a few seconds for this circuit. And the backward bounds basically say, okay, how does an error appearing here affect our initial state? An X error obviously is going to be more problematic if we have started in a computational basis state, but for the cases where we were in X and Y, the error actually isn't as bad. The Z error, conversely, doesn't really affect anything in the computational basis to begin with, which is why you have a lot of negligible terms in the Z error case here. Step 1 is really the bottleneck in this computation. So that's why in this particular case, we kind of stopped early with the forward bounds. This computation was done using 8 parallel threads and was terminated after 30 minutes. So this is roughly what you might be able to do, say, on a laptop, if you want to say, okay, I have half an hour to spare, let me see how much I can reduce my overhead of PEC. What is nice is that you can increase your classical computational resources to further reduce your overhead. So let's say rather than 30 minutes, you spend a full hour, and now you can really advance the computation of your forward bounds further into the circuit, meaning you can get tighter bounds for the error affecting your outcome. Let's say you don't just have a laptop, but you have a cluster. So now you can use 128 threads and say 30 minutes, and you can get even further. If you spend an hour, you can get even further. And you can see how more and more of the error bounds become tighter, meaning that the effect of these observables is less relevant to the expectation value that you're after. We can also plot this overhead and compare what that looks like. So here, for this particular circuit, a full PEC run has a sampling overhead that exceeds 10 to the 10, which is a large number of shots that you're unlikely to be willing to run. With the shaded light cones, we can get away more than, so we can shave off 1 order of magnitude already while keeping a remaining bias of 0. But what is nice about having these bounds available is that we can also say we can actually tolerate a remaining bias because we have a way to prioritize which errors we care about. And that means that we can actually reduce the overhead further and say, okay, I'm willing to allow, for example, up to a 10% error on my observable, and now I can shave off multiple orders of magnitude of overhead from my PEC computation. And this is really nice because it means that we can really, in a controllable manner, reduce the overhead while accounting for an error that we may be okay with. And here you can see how really spending additional classical resources allows you to push this overhead further down just by spending a bit more compute. Now, these are not the results for the 40-qubit case. This is the 20-qubit case with a shorter circuit depth. I just want to show what these results basically can look like. So here we have an equivalent 20-qubit circuit with an Rx angle of pi over 4. So we have quite fast information spreading in our circuit. We have a 2-weight observable, X on qubit 6 and Z on qubit 13. Our full PEC sampling overhead is on the order of 2,000. And if we allow a remaining bias of 10% using the shaded light cone, we can get that down to an overhead of around 150. And if we include T-Rex readout error mitigation and qubit-based post-selection, we get results that look like this. So our unmitigated data, I need to explain what this plot is. So we're plotting the expectation value as we increasingly get more randomizations of our circuit in. So let's say here you've only gathered, say, 100 randomizations. Your expectation value isn't very good yet. But the more randomizations of your circuit you get, the more data you gather, the higher confidence you get in your expectation value. The unmitigated data doesn't really change much. It has around a 20% noise-to-signal ratio, which isn't very good. If you were to try to use the full PEC overhead, you can see it fluctuates quite a bit in the beginning. At some point, it does converge, but you still have a decent standard deviation on your observables here. In contrast, if you use the shaded light cones in addition, you reach this 10% interval fairly quickly, and you can converge into this interval, and you can see that the standard deviation is really shrinking a lot. So here, you could probably improve your data even further if you were to do, say, some filtering. You can detect that here these shots apparently have been more affected by noise by inspecting this data. So if you were to filter this out, you could probably improve the data further. But the nice thing is really that the shaded light cone allows you to converge within this interval much, much quicker. OK, now let's switch gears and look at propagated noise absorption. So the shaded light cones, they really fit into the PEC workflow that I showed in the beginning. But what is nice in this entire framework is that we're not stuck with PEC. We can say, well, actually, I want to do something entirely different. Because all the pieces are modular, you can say, OK, why don't I try an entirely new error mitigation method? And that's what propagated noise absorption is doing. So here, the idea is that if we take our circuit again, where we have for every single 2-qubit layer, we have a noise model, and we have our inverse or our anti-noise channel to the left of it in order to cancel the noise, rather than doing the PEC style where we try to sample from the inverse noise through circuit randomizations, what we do in PNA is we take the inverse noise and propagate it through the circuit towards the observable, and then we absorb these inverse noise channels into our observable, giving us a new observable to measure. And this new observable will have different coefficients and different Pauli terms, but by measuring those and computing the expectation value using those coefficients, we're mitigating the noise of our circuit through the measurement of the observable. Yeah, and that's what I should have clicked before. So we have a new O tilde to measure, and by measuring its expectation value, we are mitigating for the noise in the circuit. What does that look like? So going back to the image I had before, where we have our multiple steps of our pattern, we have our target circuit that we box up, we have our noise model that we're learning. Now we perform our PNA computation, where we basically have a single function that we need to call, which is generate noise mitigating observable. Fairly descriptive name at that. We have our box up circuit, we have the target observable, and now we have our box to noise map. Basically, this is a dictionary that is saying for every single box in our circuit, what is the noise model that comes with it. And out of it, we get a new observable, which we then need to compute the bases for to insert into our samplex. But the rest of the workflow really stayed the same in the sense that we are still boxing up a circuit, learning its noise, and then using the executor to compute the randomizations of our circuit and to sample from them. And then in the end, for our expectation values, we now just have to make sure that we use the correct reverser from our PNA observable. Now, what we can do is we can, and this is data that Andrew already showed 2 days ago, but I think, again, it's nice to reiterate on these. What we can do is we can tune the truncation of our Pauli propagation, because, again, this is a costly computation. So what we have here is basically we're plotting the coefficient magnitude of an observable, the exact O tilde for this 9-qubit test case where we can actually compute the exact O tilde, versus an approximate O tilde. And when we include 80,000 terms in our Pauli propagation, we can see that we land directly on the diagonal. And that means that our approximation of O tilde is actually exact. Now, if we start to decrease the number of Pauli terms that we account for, we can start to see that our approximation becomes worse as we start to deviate from this diagonal. And if we go all the way down to 1,000, we can really see that we're spreading quite far. What is important, though, is that we can see that a decent number of terms actually still lies on the observable. So we can get away with actually measuring only the expectation values of the terms whose coefficients lie on this diagonal in order to still get a very good approximation of the expectation value of O tilde. Of course, in the case where this is a larger example, you don't know what exact O tilde is. But in practice, we find that using the largest coefficients, measuring the Pauli terms of the largest coefficients seems to work quite well. Here, we can compare against the percentage of terms to measure, and this is reiterating on that point. So we have the expectation value of O tilde, and we have an increasing number of terms that we measure. So here, our total O tilde has 10 to the 5 terms. And if we start to measure the expectation value of these different Pauli terms in our observable and compute the expectation value, initially it will be fairly poor because our original O tilde, actually, our original observable has more than a single Pauli term in it. But as we start to saturate this limit, at some point we actually get to the expected value. We can overshoot it slightly because the terms of our original observable have been rescaled to account for the noise. But we can see that we can converge to the exact value fairly quickly without having to saturate the number of terms that our O tilde contains. In practice, we can see that this works very well. So here we have a 30-qubit kicked Ising Hamiltonian. It's the same structure of circuit that I was showing before for the shaded light cones, using 30 qubits, 10 Trotter steps mirrored, and a Rx angle of pi/8. And our target observable is the weighted average of our single Z observables on all qubits. And what we can see is if we have an increasing number of Pauli terms that we're accounting for during our Pauli propagation, we can really converge to the expected outcome of 1 fairly quickly with even just 1,000 terms, which is, as I was showing you earlier in the 9-qubit example, deviating from the diagonal fairly quite a lot already. What we can also see is that the stacking of these different error mitigation techniques that we also use in the shaded light cone case applies here as well. So we can combine our propagated noise absorption with T-Rex, with post-selection, and also both of them, and you can see how that improves the expectation value that we're computing step by step, and really only combining everything allows us to really get a very good, accurate expectation value here. So to kind of recap, we're focusing on capabilities rather than features. Samplomatic is a very elaborate framework in which you can implement such error mitigation techniques. Noise Learner v3 is allowing you to give control over how you learn the noise of your circuit layers, and it gives you the confidence in how you can transfer it from the noise learning to the execution. And the executor allows you to do your entire circuit sampling on the server side without having to send a lot of data as you would have had to were you to implement these methods using the sampler primitive. And taking all of this together really allows you to really implement new error mitigation techniques with full control over every single aspect that you want. And because all of these tools are open source, we really want you to try and play with them, see how you can combine them, see how you can iterate on them, and really build new error mitigation workflows around them. And later today, we actually will give additional in-depth tutorials on both of these methods. So here I'm just including the GitHub pages for these different links. But all of these are still open areas of research. So we really want to hear feedback from you, how these help you in tackling new application areas and how you might want to build on top of them. So after lunch, we have a series of 3 tutorials. The first one will really do a deep dive into Samplomatic, which Ian was talking about earlier, but now hands-on. This will be done by Sam. And then we also have one tutorial that I will give on the shaded light cones, and then Caleb will talk about the propagated noise absorption in more depth. So we highly recommend that if you want to learn more, come see us after lunch in the L1 breakout that is in the room next door. And with that, I'd like to thank you all for your attention. And I believe now